Welcome to Topcast, and this is episode 87 if you're an audio-only listener. Otherwise, it's the discussion of Chapter 3 of The Fabric of Reality. Chapter 3 being titled Problem Solving. This is a great overview of the process of science in particular, according to the Kunian Worldview, and it's a great refutation of all the common misconceptions about how science is supposed to work. Most of those misconceptions are still prevalent today, and they come in all sorts of guises. I've mentioned this before. For example, Bayesianism is just a new incantation of the problem of induction as applied to science. So what David seems to do here in this chapter is to compile and kind of refine Popper's takedown of induction, and it's a really withering takedown here in this chapter of The Fabric of Reality. But it goes further than just a withering takedown of induction. It gives you the alternative. It gives you the correct idea about how science actually manages to generate objective knowledge about the world. And I would say that no one who actually understands what this chapter is saying can remain a Bayesian or can remain confused about what induction is supposed to be and what the problem of induction is, let alone how science really proceeds and really generates knowledge. And they would tend not to use phrases like, this evidence confirms the theory, or this makes me more confident that the theory is true, and so on, if you properly understand what's being said in this chapter. And this chapter is, of course, timely and timeless. Right now, we are in an epoch where politicians in particular are supposed to follow the science, capital T, the science. In other words, there is supposed to be a scientific consensus, and all of us should have policies based on the science, as if the science is settled, and we often talk about the settled science. But this is wrong. This is wrong because science, like every other area of knowledge, is conjectural, and at any time it can be overturned by new evidence, new theories that explain what previously seemed to be true, but in fact turn out to be, strictly speaking, false. Of course, none of this is to say we shouldn't take our best explanations seriously as our best explanations of the world, and thereby make policy informed by those best explanations. But whether or not the best explanations we have are really good explanations, well, that's another matter. Sometimes the best explanation might be something like, we don't actually really know what's going on here. We don't have a good explanation. That could be the best explanation, ironically. Whatever the case, if you want to level up your thinking, I think this chapter is a great place to start. It's a chapter that, if you are so far not familiar with the work of David Deutsch and Karl Popper, it's going to challenge your intuitions and reformulate, I would say, the way in which you do think. That happens with all of David's chapters in both of his books, of course, but this one in particular really will take the legs out from underneath you if you haven't considered carefully these particular issues before. So whether you have thought deeply about how science works, or if you haven't, if you're unfamiliar with critical rationalism or Popper's worldview, this chapter might very well blow your mind. So the chapter is called Problem Solving, and Popper actually had a book called All Life is Problem Solving, and he really meant it. If you can continue to solve your problems, then you will just keep on going on living, solving your problems. And in fact, the joy is found in perpetually solving your problems. The only reason you die is because you haven't been able to solve that problem. But it too is soluble. And in fact, if we consider life more broadly, as in the evolution of species over time, that too, on Popper's view, was an attempt at problem solving. What the genes are trying to do is to solve the problem of how to survive in a certain niche. Now, whether or not you want to push the analogy that far, I don't know. But all of us have problem situations, things that we're interested in at a particular time and place, and we're trying to sort out in order to have more fun, be more healthy, have a more flourishing life, and so on and so forth. So although any particular problem might be parochial, it might just be about you at a particular time and place, this concept of life, of problem solving, is a universal one. It's the way in which knowledge is generated. It's a certain lens through which we can view the way in which progress actually happens. Progress happens by continually identifying and then solving problems, or in other words, detecting errors and then correcting them. So all of this is a similar way of orbiting a conception of what knowledge is all about. Now, this chapter contains a lot of very deep ideas, a lot of subtle ideas, and a lot of what you might call aphorisms that I'm going to highlight as we go through. It's dense. It's counterintuitive for people who, again, are not familiar with this critical rationalist view of the way in which knowledge is generated. So it might take a while to get through this chapter as compared to some of the others, but we will persevere and we'll get there in the end, and hopefully we'll be able to clarify what Popper has said and what David has said and what my understanding of this chapter is, as always. Without further ado, let's get into it. Chapter 3. Problem solving, and David writes, I do not know which is stranger, the behaviour of shadows itself, or the fact that contemplating a few patterns of light and shadows can force us to revise so radically our conception of the structure of reality. The argument I have outlined in the previous chapter is, notwithstanding its controversial conclusion, a typical piece of scientific reasoning. It is worth reflecting on the character of this reasoning, which is itself a natural phenomenon, at least as surprising and full of ramifications as the physics of shadows. Pausing there, my reflection. So just remember that in the previous chapter called Shadows, it was essentially about the shadows being cast by, well, at first a torch, and then a laser light. When the light passes through a double slit, this famous double slit experiment, first done by Thomas Young back in the 1800s. And if you fire this single photon of light, this single particle of light at the apparatus, you end up getting an unexpected interference pattern. And through the chain of explanation that David provides in that previous chapter, go to the previous episode of The Fabric of Reality for that, what you conclude, what you are forced into concluding, the only known explanation of this is that there must be other photons that you cannot detect in this universe. In other words, the universe is stupendously larger than what we think. This is why we call it a multiverse, because there are these other universes which are approximately parallel to our own. They don't interact very often, except through these interference experiments. So this, what would otherwise might be termed an insignificant observation of the movement of single photons, leads to this stupendous conclusion that we live in a multiverse. Now, a lot of people argue against this through simple incredulity. It's like, how could it be so? How could this small amount of evidence lead to such a stupendous conclusion? But we can refer to any number of other observations like this. David makes this point elsewhere that the history of astronomy certainly is a history of seeing smudges on a photographic plate here rather than there. And that leads to the conclusion that there is a whole galaxy of stars out there. Or imagine trying to explain to the ancients that in rocks we would find evidence that rules in favour or rules out all other theories, except that there used to be these large, flightless, bird-type creatures roaming the earth millions upon millions of years ago. And that's found in rocks. Or that some of the pinpricks of light that the ancients could see in space were actually whole other worlds just like our own. And in fact, beyond that, there were pinpricks of light that could not be seen except by the use of melted sand, which arranged in a metal tube would reveal these distant objects. See, all of the knowledge that we have today seems, from a particular perspective, the perspective of an ancient, to be bizarre and ridiculous. A bizarre and ridiculous conclusion to draw on such scant evidence. And the multiverse conclusion is just another in that long lineage of strange stories that we tell about the world, which just happen to be true. Let's continue. And David writes, to those who would prefer reality to have a more prosaic structure, it may seem somehow out of proportion, unfair even, that such momentous consequences can flow from the fact that a tiny spot of light on the screen should be here rather than there. Yet they do, and this is by no means the first time in the history of science that such a thing has happened. In this respect, the discovery of other universes is quite reminiscent of the discovery of other planets by early astronomers. Before we sent probes to the moon and planets, all our information about planets came from spots of light or other radiation being observed in one place rather than another. Consider how the original defining fact about planets, the fact they are not stars, was discovered. Watching the night sky for a few hours, one sees that the stars appear to revolve about a particular point in the sky. They revolve rigidly, holding fixed positions relative to one another. The traditional explanation was that the night sky was a huge celestial sphere revolving around the Earth, and that the stars were either holes in the sphere or glowing embedded crystals. However, among the 1,000 points of light in the sky visible to the naked eye, there are a handful of the brightest which over longer periods do not move as if they were fixed on a celestial sphere. They wander about the sky in more complex motions. They are called planets, from the Greek word meaning wanderer. Their wandering was a sign that the celestial sphere explanation was inadequate. Successive explanations of the motion of planets have played an important role in the history of science. Copernicus's heliocentric theory placed the planets and the Earth in circular orbits around the Sun. Kepler discovered that those orbits are ellipses rather than circles. Newton explained the ellipses through his inverse square law of gravitational forces, and his theory was later used to predict that the mutual gravitational attraction of planets would cause small deviations from elliptical orbits. The observation of such deviations led to the discovery in 1846 of a new planet, Neptune, one of many discoveries that spectacularly corroborated Newton's theory. Pausing there, just my reflection. This word corroborate, yes, Popper uses it. It kind of means in this sense consistent with, but if you go and look it up in a dictionary, what you find is that it says something like confirm or support, which is absolutely not what is meant here. If your theory makes a prediction, for example, if you use Newton's theory of gravity to predict that the reason why Uranus is being perturbed, its orbit is being perturbed, is because there's another planet out there called Neptune. And if you go looking and you find Neptune, that does not confirm, that does not support, that does not say that Newton's theory is actually correct or true or something like that, probably true, anything like that. What it means is that there is no other theory that can do as good a job as Newton. And so Newton's theory contains some truth within it. And any theory that could not make such a prediction is therefore ruled out as inferior to what Newton's is. All of this might be summed up with the word corroborate. It's just that warning, flagging the situation that if you go to the dictionary and you look up what corroborate means, sometimes you'll see confirm or support. Explicitly not what Popper and Deutsch mean by the word. Let's continue. David writes, nevertheless, a few decades later, Einstein's general theory of relativity gave us a fundamentally different explanation of gravity in terms of curved space and time, and thereby predicted slightly different motions again. For instance, it correctly predicted that every year the planet Mercury would drift by about 1/10,000th of a degree away from where Newton's theory said it should be. It also implied that starlight passing close to the Sun would be deflected twice as much by gravity as Newton's theory would predict. The observation of this deflection by Arthur Eddington in 1919 is often deemed to mark the moment at which the Newtonian worldview ceased to be rationally tenable. Ironically, modern reappraisals of the accuracy of Eddington's experiment suggest this may have been premature. The experiment, which has since been repeated with great accuracy, involved measuring the positions of spots, the images of stars close to the limb of the Sun during an eclipse, on a photographic plate. As astronomical predictions became more accurate, the differences between what successive theories predicted about the appearance of the night sky diminished. Ever more powerful telescopes and measuring instruments have had to be constructed to detect the differences. However, the explanations underlying these predictions have not been converging. On the contrary, as I have just outlined, there has been a succession of revolutionary changes. Thus, observations of ever smaller physical effects have been forcing ever greater changes in our worldview. It may therefore seem that we are inferring ever grander conclusions from ever scantier evidence. What justifies these inferences? Pausing there, my reflection. The first thing here is that there has been a debate, even among people who identify as Popperians, about the extent to which and whether or not we are converging on anything like reality or the truth or something like that, given that it seems as though one new theory of gravity or one cosmological theory seems to utterly overturn the previous theory. And so this sometimes leads some Popperians to gravitate towards what might be called a Kunian worldview. Thomas Kuhn, a far more popular philosopher, sociologist of science, a great rival of Popper. He's the most, again, I think I've mentioned this before, he wrote The Structure of Scientific Revolutions, the most cited work in the social sciences ever, because it basically says that science goes through these revolutions, much like happens in the social sciences. And so it cuts the physical sciences down to size, and it says, well, it's not really, well, taken in a certain sense. Some people think that it means that scientific knowledge is not objective. It just goes through trends or fashions, that kind of thing. The fancy word used is paradigm. So we have a Newtonian paradigm and then we have an Einsteinian paradigm, and these two paradigms have nothing to do with one another, and one person operating in one paradigm can't see the truth of the other paradigm. They both work within a certain domain, and we can't say that we're converging on anything like reality or the truth. The problem with this whole idea is that it concentrates on what changes from theory to theory and not what remains the same from theory to theory. The simple fact is that whether you are working with Kepler or Newton or Einstein, planets still exist. This thing called gravity still exists. We just don't know the nature of it. What happens is that in Kepler, there's some reason why, call it gravity, that the planets go around the sun. When we get to Newton, we say it's a force, but he doesn't know what causes the force. We still have planets and we still have orbits. And when we get to Einstein, we still have planets, we still have orbits, we still have this thing called gravity, and we still say that it approximately obeys the inverse square law. And this is why we have approximate ellipses in terms of orbits, but we get to explain what the true nature of gravity is, so far as we know now, the curvature of space-time. So much is being preserved. It's not all overthrown. It isn't a complete revolution. Many of us like to concentrate on the fact that what we're having is an incremental change in various parts of the theory. Of course, some parts are utterly overturned, but not the entire content of our understanding of that particular concept, let alone all of our knowledge. I don't like to agree with the people who say it's a complete revolution. It's not a complete revolution. A complete revolution actually undoes everything. Everything that was good is completely cast aside, and we're implementing something else for reasons of fashion, for not a good reason. And this happens in politics, and if you were to take it seriously in science, what you would be saying is we're going to throw away even the existence of planets, even the existence of orbits, as we change from one theory of gravity to another. But we're not. We're not doing that at all. We're throwing away some things, replacing them with others, tweaking things, coming to a deeper understanding, but we're preserving a whole bunch as well. So that's one thing. The other thing is, David says, what justifies these inferences? Now, I would encourage everyone to get a hold of the audio book of The Fabric of Reality. It's relatively new, and at the beginning of that audio book is an introduction by David Deutsch himself. And in that introduction, recorded 20 years after he first wrote the book, he says that he would put certain things differently. And one of the key things that he would put differently is use of the word justifies. And it comes up again in chapter 7 of The Fabric of Reality, where he says it really needs to be interpreted as an indication of the morally right thing to do, or the methodologically right thing to do. That's what he means by justifies. Unfortunately, it can have echoes of justification. It doesn't mean that when you say what justifies such and such, that you are saying what demonstrates as true such and such. That's not what he means. Now, I tend to think that when I read The Fabric of Reality and I read David's use of the word justifies, I'm reminded, and I hope that David doesn't regard this as an insult, I'm reminded what Wittgenstein said of his own philosophy. After all, Wittgenstein, if you recall, some of my other podcasts I've talked about this, Wittgenstein argued that there are no such thing as philosophical problems, and going further, that therefore there's no good reason for philosophy. All of our knowledge can come to us via science and perhaps mathematics, but you have no need really for philosophy. And so then, of course, people might object to Wittgenstein himself and say, well, hold on, Wittgenstein, you are a philosopher and you have a philosophy. Are you saying of your own philosophy that it's useless? And he said, kind of. It's like a ladder in order to get yourself out of a deep well if you've fallen in, the deep well being philosophy. What you do is you use Wittgenstein's philosophy to climb your way out of the well, and then once you're out of the well, you can also cast aside the ladder. You don't even need that anymore either. Clever little quip. But I like to actually think that that's the way to understand David's use of the word justify. Because if you really do understand what's being said in the fabric of reality, you realize there is no way in which you can actually justify as true anything at all. You can't justify stuff in science or anywhere else. And by the end of the book, you understand that. So that's what the word justify is. It's like David gives you the ladder in order to throw away this justificationist scheme, and so you can even throw away the word to a large extent as well. However, in order to get there, you have to grant people who don't yet agree with you the word justify, okay? So because it takes a while to undo these things. It's like the word confirm or support and various other things. You know, if I'm speaking with someone that hitherto is completely unfamiliar with Popper and that whole way of speaking, I might very well use the word confirm and support and that kind of thing until such time as I can help them to understand the Popperian worldview. And once they do, then you can turn around and say, you see, you needed to use the word support, and you can never actually confirm a theory. So you can do away with those entire concepts. But until such time as you're both speaking the same philosophical language, you're going to have to meet them halfway. And so that's the way in which I interpret justify in this book. So anyway, David goes on to say, quote, can we be sure that just because a star appeared millimetrically displaced on Eddington's photographic plate, space and time must be curved? Or that because a photodetector at a certain position does not register a hit in weak light, there must be parallel universes? Indeed, what I have just said understates both the fragility and the indirectness of all experimental evidence, for we do not directly perceive stars, spots on photographic plates, or other external objects or events. We see things only when images of them appear on our retinas, and we do not perceive those images until they have given rise to electrical impulses in our nerves, and those impulses have been received and interpreted by our brains. Thus, the physical evidence that directly sways us and causes us to adopt one theory or worldview rather than another is less than millimetric. It is measured in thousandths of a millimetre, the separation of nerve fibres in the optic nerve, and in hundredths of a volt, the changes in electric potential in our brains, in our nerves, that make the difference between our perceiving one thing and perceiving another. Pausing there, just my reflection on this. If you hear the phrase, evidence is theory laden, or something like that, this is one sense in which that phrase is cashed out. When you hear that phrase, evidence is theory laden, or perception is theory laden, any of those things, this is what is meant by that. That when you say you've seen something, it's not a direct experience, because we know, we have a theory of sight and how it works, and it's complicated. It's not simply that you look outside and you see the sun shining. What that means is photons of light have actually entered your eyes, and those photons of light have fallen upon your retina, which have given rise to, well, actually, it's really complicated. It goes through, causes chemical changes in the photosensitive cells of the eye, in the light-sensitive cells of the eye, and that gives rise to electrical impulses, which travel along the optic nerve and then to the brain. So this whole process is what seeing is. It is a complicated process. Speaking of perceptions, now your perception might change a little bit, because I've decided that I'm going to just slightly alter my setup here so that the audio sounds a bit better. When I record video, the audio sounds one way, I've noticed, and when I don't, by plugging my microphone directly into my computer, it sounds better. You don't need to hear all the details, I suppose. Anyway, you won't be seeing my face again for the remainder of this episode. This is just an experiment. I want to see, here the difference between the audio-only type version and the video and audio type version. An overwhelming majority of people only listen to me. They don't watch me. I think it's like a ratio of 10 to 1 almost. And so just to make things a little bit easier for me, I'm just going to record audio only for the remainder of this, with the exception that there are a few images to come. And the reason there are images to come is because David provides them in the book. And so I want to show you those images. So they'll be important. But for now, I'm just switching to audio only. Okay, so here we are back with the audio only version. Now, to my ear, this sounds better. And it's also rather easier for me to edit. However, if I get feedback to say that people would prefer the video, then I will continue to do that. And I'm not going to stop doing that, at least for the introductions, I would say. But for rather the majority of the podcast, it makes things a lot easier. And I think it actually sounds better if I'm just doing audio for various technical reasons. Anyway, let's keep going. I'm up to the point in the book where David writes, quote, "However, we do not accord equal significance to all our sensory impressions. In scientific experiments, we go to great lengths to bring to our perceptions those aspects of external reality that we think might help us to distinguish between rival theories we are considering. Before we even make an observation, we decide carefully where and when we should look and what we should look for." Pausing there, my reflection. Okay, this idea that we look for observations which can decide between rival theories is so important. This is the concept of a crucial test. And David has written an absolutely wonderful paper all about this called The Logic of Experimental Tests, with a particular emphasis on Everettian quantum theory. But you can actually read through the paper without ever bothering with the quantum theory part unless you're a quantum physicist, because it explains what the point of a crucial test is. This particular jewel in the crown, if you like, of the scientific method, insofar as there is a scientific method. But this point of crucial test is where you've got two rival theories, there is an observation which will rule out one of them, leaving you with only one theory that explains the evidence before you. This is where certain subjects, let's just call them out, let's say psychology, sometimes gets things wrong. If you're going around collecting data and you're trying to extrapolate from the data, but you don't actually have a theory to begin with, you're missing the point of science. You're missing the point of collecting data. Collecting data essentially amounts to doing an experiment, actually going out into the world, making observations. But in psychology, rather too often, they simply collect data and then don't have an explanation before they begin collecting the data. Here's a caricature or a cartoonish version of such a psychological study. And the only reason I know about this is because in schools of certain kinds, you can actually study a subject called psychology. Now, what they do there is they actually can force the students to undertake an experimental study. And what they do is they do things like, well, let's check how impulsive different groups of people are. So let's check how impulsive people are given their gender. So we'll check how impulsive a male person is versus a female person. And the way in which you might do this, well, the standard thing of let's put them in a room with a cake for a little while and let's see who eats the cake first. And let's say you have a statistically significant number of occasions where it's the male that takes a bite out of the cake before the female does. And so on this basis, you then draw the conclusion, therefore males are more impulsive than females. But you haven't actually at any point figured out the reason why. All you're saying is that there is a correlation that you've discovered. There's no explanation there though. Is it really the maleness versus the femaleness? Is that the thing? Is it something deeper than that? Is it something about the amount of testosterone? And if it is the amount of testosterone, why? By what mechanism? Or is it something deeper still than that? Is it in the genes? If it is in the genes, how so? Is it something to do with the way in which males are raised as children that causes to be more impulsive? Which could rule out this whole idea that males are more impulsive than females in the first place. It could simply be a cultural thing, having nothing to do with males whatsoever, and having everything to do with ideas. This is the poverty of explanationless science. You can't do an experiment, a legitimate experiment, a useful experiment, until such time as you have an explanation. And the explanation is then going to be tested against reality. That's what the experiment is. And in fact, it's even worse than this, because if you have only one explanation and you do an experiment and the experiment disagrees with your explanation, there is no way to refute, throw away, discard the explanation. After all, how then do you go about explaining the observations you are making? And how do you know that it's not the experimental method that is falling apart that is the reason for the disagreement? This is the Duhem-Quine thesis again, and Popper was fully aware of it, and Deutsch is fully aware of it, and anyone who is a proper Popperian is fully aware of it, that sometimes you can do an experiment, and although the experiment disagrees with the explanation, with the scientific theory, that doesn't necessarily, it doesn't logically mean that the theory is wrong, especially in a case where you only have one explanation. The only explanation, the scientific explanation, which is why David has said there, quote, and I'll just continue reading, "Before we even make an observation, we decide carefully where and when we should look and what we should look for. Often we use complex, specially constructed instruments such as telescopes and photomultipliers. Yet however sophisticated the instruments we use, and however substantial the external causes to which we attribute their readings, we perceive those readings exclusively through our own sense organs. There is no getting away from the fact that we human beings are small creatures with only a few inaccurate, incomplete channels through which we receive all information from outside ourselves. We interpret this information as evidence of a large and complex external universe or multiverse. But when we are weighing up this evidence, we are literally contemplating nothing more than patterns of weak electric current trickling through our own brains." Pausing there, my reflection. Now you will notice, if you are a Deutsch superfan, so to speak, that he has used the phrase there, weighing up this evidence. And again, that might set off alarm bells. I'm sure he doesn't literally mean, in fact, we know he doesn't literally mean weighing up this evidence, because he explains this in The Beginning of Infinity. What would be meant there is just the prosaic idea of considering this evidence. Okay, we're not weighing some evidence against others. It's just a turn of phrase. We're not actually weighing up by some process. After all, evidence doesn't have a particular weight. Either the evidence agrees with an explanation or it doesn't. And if it doesn't, then we have a problem and we have to go about solving that problem. If we have two theories and it agrees with one explanation but does not agree with the other, the one that it doesn't agree with is refuted. Typically speaking, it can always logically be the case that the experiment has been performed incorrectly. It always comes down to explanations, an argument, and having a good understanding of what's going on throughout the experiment. But especially in cases where you only have one theory and you have one experiment which disagrees with your one theory, you simply have a problem. You don't know what's going wrong. You're not in a position to say, therefore the theory is incorrect. You don't know. You don't know if the theory, the explanation is incorrect, or your theory of the experiment is incorrect. The theory of how the instrument that is being used in the experiment is working. That it's all theories, everything. Observation is theory-laden, as we say. Perception is theory-laden. The evidence is theory-laden. The whole world is theory-laden. It's all being interpreted by your mind. And back to the book. What justifies the inferences we draw from these patterns? It is certainly not a matter of logical deduction. There is no way of proving from these or from any other observations that the external universe or multiverse exists at all, let alone that the electric currents received by our brains stand in any particular relationship to it. Anything or everything that we perceive might be an illusion or a dream. Illusions and dreams are, after all, common. Solipsism, the theory that only one mind exists and that what appears to be external reality is only a dream taking place in that mind, cannot be logically disproved. Reality might consist of one person, presumably you, dreaming a lifetime's experiences. Or it might consist of just you and me, or just the planet Earth and its inhabitants. And if we dreamed evidence, any evidence, of the existence of other people, or other planets, or other universes, that would prove nothing about how many of those things there really are. Pausing there, just my reflection. So this idea of solipsism, this idea that only you exist and everything's being dreamed into reality, it just keeps cropping up again and again in the history of philosophy. One of the earliest mentions is, of course, Plato's cave, this idea that what he got right, of course, in Plato's cave is that we only have access to our senses. We don't have direct access to reality. But taken too far, it means that perhaps external reality doesn't even exist at all, that all you have are just your senses. Descartes came up with a method of doubt, and he thought that, well, it could be possible that there would be this evil demon that might be deceiving you, this all-powerful, almost all-powerful demon that could be tricking you into thinking the external reality actually exists, some sort of creature with superpowers. The movies, The Matrix, are all about this as well, that perhaps we're sitting inside of some sort of computer simulation type thing. And taken to an even more extreme, we have Nick Bostrom's simulation hypothesis. All of these are logically equivalent. They're what Luli Tannett has called supernaturalism, this idea that you're just appealing to some idea that is a priori beyond our capacity to refute. Well, refute experimentally anyway, because it puts itself beyond what physics can possibly probe. In other words, beyond physical law or natural law. It's supernatural, supernaturalism. I think that's exactly right. We can ignore all these things because we can refute them, not by experiment, but by argument, which is where David's going to get to. And so David picks up the discussion where he writes, quote, "Since solipsism and an infinity of related theories are logically consistent with your perceiving any possible observational evidence, it follows that you can logically deduce nothing about reality from observational evidence. How then could I say that the observed behaviour of shadows rules out the theory that there is only one universe, or that eclipse observations make the Newtonian worldview rationally untenable? How can that be so? If ruling out does not mean disproving, what does it mean? Why should we feel compelled to change our worldview, or indeed any opinion at all, on account of something being ruled out in that sense? This critique seems to cast doubt on the whole of science, on any reasoning about external reality that appeals to observational evidence. If scientific reasoning does not amount to sequences of logical deductions from the evidence, what does it amount to? Why should we accept its conclusions? This is known as the problem of induction." Pausing there, my reflection. Okay, so let's just recap that here so that we have in mind a clear understanding of what we mean by the problem of induction. So the story goes. Typically, if you ask someone who is familiar, let's say, with science, but not necessarily with the philosophy of science, what we do in science to produce knowledge of the physical world, what they might say sometimes is we make observations, and from those observations we deduce explanations. We read from the book of nature, so to speak. We observe the world, and then from those observations logically derive a theory about what's going on. And in fact, by the way, this is what the Bayesians kind of think. They just think that they derive probably true theories rather than absolutely true theories. And they can calculate how confident they are in the theory that they deduce from these observations. But whatever the case, this problem of induction, as it was classically framed, was something like, well, you observe day after day, morning after morning, the sun rising, and therefore you deduce, in some way, the theory that the sun will continue to rise tomorrow. Now, of course, that's merely a prediction. That's not an explanation. We're about to get to that as well. As David goes on to say, quote, "The name, problem of induction, derives from what was, for most of the history of science, the prevailing theory of how science works. The theory was that there exists, short of mathematical proof, a lesser but still worthy form of justification called induction." Pausing there, just my reflection again. This word induction has lots of different meanings. Firstly, there is a deductive method in mathematics called proof by induction, and it is deductive. So it's important not to get the two confused because they're actually opposites of one another. One is a logical method of proof in mathematics. What typically happens, by the way, and this happens in high school mathematics, among other things. What you do is you're given a formula. You then show that the formula works for n equals 1. It's valid for n equals 1. Then you assume that it's true for some general case, n equals k. And then you show that given that assumption, it actually works for n equals k plus 1. And given that you've already shown that it works for the n equals 1 case, then substituting in n equals 1 for n equals k and showing that therefore it works for 1, then 2, and on into infinity, given the formula you've just got, you've proved via the method of induction that this formula works for all possible cases of n. Now, that's perfectly valid. That is a perfectly valid way of doing mathematical proof. It's deduction. By unhappy coincidence, I haven't looked into the history of this, but by unhappy coincidence, I guess that the philosophers of science early on went, well, there must be a similar method in science. We're going to use the same word, induction, where we can prove such a thing holds for all cases, often to infinity. This doesn't work for a whole bunch of reasons because unlike with a mathematical formula, which is necessarily true, it's predictable in necessarily true ways, the physical world is not like that. It's not like that at all. We know this. We know that tomorrow doesn't look like yesterday. Things change in the physical world all the time. We don't understand all the reasons why, by the way. But certainly the laws of physics mandate that not everything that happens from day to day to day will be precisely the same. There are other forms of induction as well, by the way. This word induction, it also works in physics in various ways. It has different meanings. There's charging something by induction. So if you have an electric charge on one object and you bring it close to another object, which is hitherto not yet charged, and in bringing these two things closer, what happens, the neutral one, well, let's say you've got an object A. The way that electrical induction works? Well, static electrical induction anyway. Imagine two spheres, metal, one of which has a negative electric charge. You've charged it by some method. And a second sphere, which is neutral, you bring them close to each other, but not touching. Not touching. And if you have them such they're not touching and they're both metal spheres, the first of which is negative, well, it will push away the negative charges on the second sphere. And you can then discharge those negative charges on the second sphere because you have this dipole. And when you do the discharging, this is called charging by induction. Now, there's also other kinds of electrical induction as well that go on. There's also the induction that happens when an employee enters a new workplace for the first time. They undergo a process of induction. So induction is curious in that it has very, very many different meanings that have very little to do one with another. But this kind of induction, this induction in the philosophy of science is about if you can't derive logically, if you can't prove that a particular theory is true given the evidence, perhaps you can get almost true, highly confident, something like that. And so we don't have deduction, but we have induction, which is almost as good. That's what was hoped for in science. David writes, induction was contrasted on the one hand with the supposedly perfect justification provided by deduction, and on the other hand, with supposedly weaker philosophical or intuitive forms of reasoning that do not even have observational evidence to back them up. In the inductivist theory of scientific knowledge, observations play two roles. First, in the discovery of scientific theories, and second, in their justification. A theory is supposed to be discovered by extrapolating or generalizing the results of observations. Then, if large numbers of observations conform to the theory and none deviates from it, the theory is supposed to be justified, made more believable, probable, or reliable. This scheme is illustrated in this picture that I'm putting up on the screen, or figure 3.1 in the original book. Just pausing there, my reflection on this. I've written an article that's on my website, and you can just Google my name, Brett Hall Induction, and it should come up for you. And it's an attempt to show that precisely that sentence there that David writes, where he said, quote, if large numbers of observations conform to the theory and none deviates from it, the theory is supposed to be justified, made more believable, probable, or reliable. And my favourite example of this is anyone with a thermometer and a stove and a pot of water can do the experiment where you turn on the stove, which typically as a relatively constant source of heat, and monitor the temperature over time. And if you plot a graph of the temperature versus the time, and you have no clue, or you pretend to have no clue, about what's going to happen next, you will notice a wonderfully linear trend, or very close to linear anyway. For example, maybe every minute, the temperature of the water goes up by 10 degrees Celsius. And if you monitor the temperature between, 20 degrees Celsius up to 80 degrees Celsius, you get this lovely trend line. And you could monitor it every single degree that it rises. What does this suggest? Well, it suggests that if you think induction is a thing, then you can extrapolate the theory that as you heat the water, it continues to rise in temperature. Now, until you boil the water, you don't know that at 100 degrees Celsius, something special and unexpected happens. The temperature of the water doesn't continue to rise. But you only know that. You would only know that observation if you actually ever got to the point where you reach the boiling point of water. You can never rule out that there's not going to be a surprising observation out there like the boiling of water. So anyway, I think that is proof enough, so to speak, refutation enough at least, that induction cannot possibly be the way that science works. Putting aside what David's about to say next, that it's not even predominantly about extrapolation and prediction. That's just a small part. And anyway, you can't make the prediction until you have an explanatory theory behind you. Let's keep going. David writes, quote, "The inductivist analysis of my discussion of shadows would therefore go something like this. We make a series of observations of shadows and see interference phenomena. Stage 1. The results conform to what would be expected if there existed parallel universes which affect one another in certain ways, but at first no one notices this. Eventually, stage 2, someone forms the generalization that interference will always be observed under the given circumstances and thereby induces the theory that parallel universes are responsible. With every further observation of interference, stage 3, we become a little more convinced of that theory. After a sufficiently long sequence of such observations, and provided that none of them ever contradicts the theory, we conclude, stage 4, that the theory is true. Although we can never be absolutely sure, we are, for all practical purposes, convinced. It is hard to know where to begin criticising the inductivist conception of science. It is so profoundly false in so many different ways. Perhaps the worst flaw, from my point of view, is the sheer non sequitur that a generalised prediction is tantamount to a new theory. Pausing there, going back and just reading that's really important. The sheer non sequitur that a generalized prediction is tantamount to a new theory. Okay, so what David's saying there is that just making a prediction, so if you're observing, again, classic example rather, the sun rising each day, and on that basis you say, therefore the sun will rise tomorrow, that's not a new explanatory theory. You haven't explained anything. You're just saying what will happen tomorrow. But you've never said why. You haven't said why. That whole thing, the black swan thing, you're just observing white swan after white swan after white swan, and therefore you conclude on that basis that all swans are white. Well, that's not a theory either. That's not really a part of science, saying all swans are white. We want to know why. Why are swans white? Why can't there, for example, be black swans, even though there are? That's not what the science of ornithology, the study of birds, is about. It's about trying to have an understanding of the commonalities between different bird species, what a bird is as distinct from a mammal, and so on and so forth. It's not all swans are white. It's not all X or Y, or the sun will continue to do this tomorrow, or those things are derivations from good explanations, which we don't yet have on this conception of how science works. But we're about to get there in the Popperian view. So David goes on to say, like all scientific theories of any depth, the theory that there are parallel universes simply does not have the form of a generalization from the observations. Did we observe first one universe, then a second, and a third, and then induce that there are trillions of them? Was the generalization that planets will wander around the sky in one pattern rather than another equivalent to the theory that planets are worlds in orbit round the sun and that the Earth is one of them? It is also not true that repeating our observations is the way in which we become convinced of scientific theories. As I have said, Theories are explanations, not merely predictions. If one does not accept a proposed explanation of a set of observations, making the observations over and over again is seldom the remedy. Still less can it help us to create a satisfactory explanation when we cannot think of one at all. Pausing there, my reflection. It's interesting in the history of astronomy as well. If you look at people trying to explain, astronomers trying to explain early on how the solar system formed, the theory of our solar system actually reached out beyond the solar system to other stars. So the story here is that around our sun coalesced all the other planets, which formed from that original gas and dust cloud out of which the sun formed as well. And so did the other stars out there. Why do I bring this up? Well, we hadn't yet observed any other planets out there orbiting any other stars until I think 1994. I think that was the first time we saw it. If it wasn't then, it was very close to then. Certainly we hadn't actually seen with our telescopes any evidence of planets orbiting other stars prior to, let's say, 1980. But theories of solar system formation were absolutely there and suggested there should be planets orbiting most stars out there. That was already thought as being the case. But the theory that we had of those planets also said that with the current telescope technology, we couldn't observe them. They had to invent new techniques in order to observe the planets that they predicted and thought were there. So it wasn't like we were observing planet after planet after planet, orbiting star after star after star in order to reach the conclusion that therefore there are planets orbiting most stars. No, we already had the theory about solar system formation, which applied not only to our solar system, but also to all other stars out there. That's how science works. We have the conjectured creative explanation, which reaches out from the thing we're observing to all the unobserved stuff. And then maybe later we can figure out ways to observe that unobserved stuff, or hitherto unobserved stuff, as we did with extrasolar planets. David goes on to say, as I have said, theories are explanations, not merely predictions. If one does not accept a proposed explanation of a set of observations, making the observations over and again is seldom the remedy. Still less can it help to create a satisfactory explanation when we cannot think of one at all. And just to repeat what David said there, as I have said, theories are explanations, not merely predictions. If one does not accept a proposed explanation of a set of observations, making the observations over and over again is seldom the remedy. Still less can it help us to create a satisfactory explanation when we cannot think of one at all. Furthermore, even mere predictions can never be justified by observational evidence, as Bertrand Russell illustrated in his story of the chicken. Okay, pausing here. I'm just going to tell this in my own words, just to make it faster than merely reading it. So this idea of Russell's chicken was the parable of Russell's chicken, which I think I've told maybe a dozen times now in this podcast series. The idea is this farmer is keeping a chicken, and the chicken is being fed day after day after day. And so the chicken, who's an inductivist reasoner of a kind, thinks that he's going to continue to be fed day after day after day. Well, he's sorely disappointed when on Christmas Eve or something like that, his neck is wrung and he's killed and baked and eaten by the farmer. Now, what does this say? Well, it says that number one, you already need a theory in mind, don't you? You need to have the theory that the farmer has some sort of benevolent feelings towards you if you're the chicken being fed day after day after day. But there's another theory that is consistent with those observations, perfectly consistent, which is that the farmer is fattening you up to slaughter you for Christmas dinner. And an infinite number of other explanations as well as to why you're being fed day after day after day. The thing is whether or not you have a good explanation and can be experimentally tested in some way. What David says all about this in his way is that this disappointment experienced by Russell's chicken has also been experienced by trillions of other chickens. This inductively justifies the conclusion that induction cannot justify any conclusions. However, this line of criticism lets inductivism off far too lightly. It does illustrate the fact that repeated observations cannot justify theories, but in doing so, it entirely misses or rather accepts, a more basic misconception, namely that the inductive extrapolation of observations to form new theories is even possible. Okay, say that again. That the inductive extrapolation of observations to form new theories is even possible. In fact, it is impossible to extrapolate observations unless one already has placed them within an explanatory framework. For example, in order to induce its false prediction, Russell's chicken must first have had in mind a false explanation of the farmer's behaviour. Perhaps it guessed that the farmer harboured benevolent feelings towards chicken. Pausing there, my reflection. Yes, so the idea is you start with theories. You must have a theory to begin with before you can make an extrapolation. So in this case, the theory was, it's almost like you're assuming the conclusion. You're assuming, okay, the farmer is benevolent. Okay, that's the idea. So therefore, the farmer will continue to feed the chicken. Well, why is the farmer continuing to feed the chicken? Because it's benevolent. It's this wonderfully self-contained little thing. But whatever the case, you've already got the theory there. The theory is already in hand. It's not observations leading to the theory. No, it's a theory that explains the observations, or purportedly explains the observations. In fact, gets it quite wrong. It's a false explanation. Absent a theory, you're not really saying much. Like if I go back to the sun has risen every day of my life, let's say, and I say, well, on that basis, therefore, the sun will rise again tomorrow. What problem am I solving? Is the problem, should I expect the sun to rise tomorrow? And if the answer is yes, why? Because it's risen every day previously? How does that follow? It can follow only if I have an explanation as to why all times in the past should resemble all times in the future. You know, for example, in the real case, you know, at this particular place on the Earth is rotating, and therefore that causes the sun to appear on the horizon approximately every 24 hours. But of course, we know it's completely false if you go, you know, up to the Arctic Circle or something like that. I'm skipping a part, and David goes on to explain more about Russell's chicken. You know, on the one hand, you can say Russell's chicken extrapolates that he's going to continue to be fed every single day based on the fact that he has thus far been fed every single day. And on the other hand, if he has a different theory, that he's being fed every single day only because he's being fattened up so that he can be slaughtered, well, you've got the same set of observations, you know, namely on being fed every single day, leading to two contradictory theories. So what does David say about that? He goes on to write, quote, "The fact that the same observational evidence can be extrapolated to give two diametrically opposed predictions according to which explanation one adopts, and cannot justify either of them, is not some accidental limitation of the farmyard environment. It is true of all observational evidence under all circumstances. Observations could not possibly play either of the roles assigned to them in the inductivist scheme, even in respect of mere predictions, let alone genuine explanatory theories. Admittedly, inductivism is based on the common sense theory of the growth of knowledge that we learn from experience, and historically it was associated with the liberation of science from dogma and tyranny. But if we want to understand the true nature of knowledge and its place in the fabric of reality, we must face up to the fact that inductivism is false, root and branch. No scientific reasoning, and indeed no successful reasoning of any kind, has ever fitted the inductivist description." Pausing there, my reflection. Yes, so of course we have this idea, which is also known as empiricism, that it at least gets something right. Okay, the something that it gets right is better to learn from experience, better to learn from an encounter with reality. How is that better? Better than what? Better than authority, better than just opening up your scripture, let's say, or listening to the man wearing the dress, the priest or whatever, listening to what they say and just doing what they say, okay? Which is certainly better than just making it all up on your own constantly as well, okay? So there are there are degrees of getting things wrong, so to speak, trying never to learn anything and never listen to anything and never to observe anything. That's one level of error. Thinking that one particular person or one particular book has all the answers, that's another level. At least you're taking into account the ancient wisdom, perhaps. And then there is, of course, well, let's actually get feedback from reality in some way, shape or form. But if you think that getting feedback from reality in the form of just repeatedly observing the same thing over and over again is the way that it works, that's wrong as well. So all of those ways aren't as good at all. They don't capture the truth anywhere near like the critical rationalist way, the Popperian view of observations are about ruling between competing theories, okay, which is what we're about to get to. David goes on to write, quote, "What then is the pattern of scientific reasoning and discovery? We have seen that inductivism and all other prediction-centered theories of knowledge are based on a misconception. What we need is an explanation-centered theory of knowledge, a theory of how explanations come into being and how they are justified, a theory of how, why, and when we should allow our perceptions to change our worldview. Once we have such a theory, we need no separate theory of predictions, for given an explanation of some observable phenomenon, it is no mystery how one obtains predictions, and if one has justified an explanation, then any predictions derived from that explanation are automatically justified too." Pausing there, my reflection. Now remember, of course, David Deutsch is the person that figured out what a good explanation is, and therefore a way of distinguishing between different explanations, this hard-to-vary criterion, which meant that, well, people make discoveries throughout their life, and so between the time of writing this, The Fabric of Reality, and the Beginning of Infinity, apparently he's created the good way of delineating between good and bad explanations, which makes this talk of justification redundant. Like I say, you could view it as being Wittgenstein's ladder, allowing you to climb out of the well of justificationism, and once you're out of that well, you can just discard the ladder and you don't need to use the word anymore. But better yet, read this in light of the Beginning of Infinity. Just consider that the Beginning of Infinity, the content there, explains what really a good explanation is. So we don't have to worry about justifying explanations. We just have to worry about what a good explanation is compared to a bad explanation or a non-explanation. And therefore, if we have competing good explanations at a particular point in time, what means by which we will refute one and not the other. And in science, of course, that's the crucial experiment. Anyway, here David goes on to write, "Fortunately, the prevailing theory of scientific knowledge, which, in its modern form, is due largely to the philosopher Karl Popper, and which is one of my four main strands of explanation of the fabric of reality, can indeed be regarded as a theory of explanations in this sense. It regards science as a problem-solving process. Inductivism regards the catalogue of our past observations as a sort of skeletal theory, supposing that science is all about filling in the gaps in that theory by interpolation and extrapolation. Problem solving does begin with an inadequate theory, but not with the notional theory consisting of past observations. It begins with our best existing theories. When some of those theories seem inadequate to us, and we want new ones, that is what constitutes a problem. Thus, contrary to the inductivist scheme shown in figure 3.1, scientific discovery need not begin with observational evidence. But it does always begin with a problem. By a problem, I do not necessarily mean a practical emergency or a source of anxiety. I just mean a set of ideas that seems inadequate and worth trying to improve. The existing explanation may seem too glib or too laboured. It may seem unnecessarily narrow or unrealistically ambitious. One may glimpse a possible unification with other ideas. Or a satisfactory explanation in one field may appear to be irreconcilable with an equally satisfactory explanation in another. Or it may be that there have been some surprising observations, such as the wandering of planets, which existing theories did not predict and cannot explain. This last type of problem resembles stage 1 of the inductivist scheme, but only superficially. For an unexpected observation never initiates a scientific discovery unless the pre-existing theories already contain the seeds of the problem. For example, clouds wander even more than planets do. This unpredictable wandering was presumably familiar long before planets were discovered. Moreover, predicting the weather would always have been favourable to farmers, seafarers and soldiers, so there would always have been an incentive to theorise about how clouds move. Yet it was not meteorology that blazed the trail for modern science, but astronomy. Observational evidence about meteorology was far more readily available than in astronomy, but no one paid much attention to it, and no one induced any theories from it about cold fronts or anticyclones. The history of science was not crowded with disputes, dogmas, heresies, speculations, and elaborate theories about the nature of clouds and their motion. Why? Because under the established explanatory structure for weather, it was perfectly comprehensible that cloud motion should be unpredictable. Common sense suggests that clouds move with the wind. When they drift in other directions, it is reasonable to surmise that the wind can be different at different altitudes, and is rather unpredictable, and so it is easy to conclude that there is no more to be explained. Some people, no doubt, took this view about planets and assumed that they were just glowing objects on the celestial sphere blown about by high-altitude winds, or perhaps moved by angels, and that there was no more to be explained. But others were not satisfied with that, and guessed that there were deeper explanations behind the wandering of planets, so they searched for such explanations and found them. At various times in the history of astronomy, there appeared to be a mass of unexplained observational evidence. At other times, only a scintilla, or none at all. But always, if people had chosen what to theorize about according to the cumulative number of observations of a particular phenomena, they would have chosen clouds rather than planets. Yet they chose planets, and for diverse reasons. Some reasons depended on preconceptions about how cosmology ought to be, or on arguments advanced by ancient philosophers, or on mystical numerology. Some were based on the physics of the day, others on mathematics or geometry. Some have turned out to have objective merit, others not. But every one of them amounted to this: it seemed to someone that the existing explanations could and should be improved on. One solves a problem by finding new or amended theories, containing explanations which do not have the deficiencies, but do retain the merits of existing explanations. This figure 3.2 from the book, shows that after a problem presents itself, which is stage 1, the next stage always involves conjecture, proposing new theories, or modifying or reinterpreting old ones in the hope of solving the problem. That's stage 2. The conjectures are then criticised, which, if the criticism is rational, entails examining and comparing them to see which offers the best explanations according to the criteria inherent in the problem, which is stage 3. When a conjectured theory fails to survive criticism, that is, when it appears to offer worse explanations than other theories do, it is abandoned. If we find ourselves abandoning one of our originally held theories in favour of one of the newly proposed ones, which is stage 4, we tentatively deem our problem-solving enterprise to have made progress. I say tentatively because subsequent problem-solving will probably involve altering or replacing even these new, apparently satisfactory theories, and sometimes even resurrecting some of the apparently unsatisfactory ones. Thus, the solution, however good, is not the end of the story. It is a starting point for the next problem-solving process, which is stage 5. This illustrates another of the misconceptions behind inductivism. Just pausing there, my reflection. This is reminiscent of, now I'm going to have to go from memory here, of a quotation from Popper. And he said, words to the effect anyway, I'm going to mangle the exact quotation, but something to the effect of, I think there is only one way to do science, or any kind of inquiry for that matter, and that is to fall in love with a problem, until such time as you solve it, at which point you will find a whole family of new daughter problems. In other words, if you find a problem you're really interested in and you solve it, you will find that in solving that problem, it doesn't end your quest there. In fact, it reveals, it gives birth to, if you like, it gives rise to all these other more interesting problems as well. This is the history of science, for example. In solving the problem of what's the correct theory of gravity, or the more correct theory of gravity, Newton's theory of gravity or Einstein's theory of gravity, once we figure out we've solved the problem, it's Einstein's theory of gravity, we then have a whole bunch of other new problems. What can we use this new theory of gravity for? What does it permit, or what does it prohibit? What does it allow? All these new kinds of technologies based upon this new theory of gravity. So we end up with a whole bunch of new problems. That quest for identifying problems and solving those problems, thereby growing knowledge, is an unending quest. And on this point, David writes, and this is, I think, where we'll end it for today. As he said, the solution, however good, is not the end of the story. It is a starting point. And he goes on to say, This illustrates another of the misconceptions behind inductivism. In science, the objective of the exercise is not to find a theory that will, or is likely to, be deemed true forever. It is to find the best theory available now, and if possible, to improve on all available theories. A scientific argument is intended to persuade us that a given explanation is the best one available. It does not and could not say anything about how that explanation will fare when, in the future, it is subjected to new types of criticism and compared with explanations that have yet to be invented. A good explanation may make good predictions about the future, but the one thing that no explanation can even begin to predict is the content or quality of its own future rivals. Just pausing there. End of the reading for today. Note that really important limitation upon the growth of knowledge that David really emphasizes in the beginning of Infinity, but here it is here in the Fabric of Reality, that no theory today, no explanation we have, can predict the content of its successors. That would be to predict the growth of knowledge, something that cannot be done. And this is why, by the way, we can't predict what people will do moment to moment. People are knowledge creators. They're inherently unpredictable. They use their capacity to generate knowledge to come up with the subsequent theories. But you can't predict the content of those subsequent theories. If you did, you would have it in hand already. So it wouldn't be a prediction. It would be a theory that you already have. This is why we say it's inherently unpredictable. If it was predictable, if the growth of knowledge was predictable, then suddenly, logically, you would have a prediction of the future knowledge that is to come. But that's not possible. If it was possible, again, it would mean that you've generated that knowledge now. And so you'd have it now. So it wouldn't be a prediction in the first place. It's such a subtle point, easily missed. A prediction is about a future state of affairs. But if you're saying that the content of future knowledge is X, Y, and Z, and X, Y, and Z is only supposed to be discovered in the future at some point, but you've discovered it now, how is that a prediction? That's just a statement of the knowledge that you have now, not the knowledge that you will have in the future. It's the knowledge that you have now. So it ceases to be a prediction. It's a curious outworking of this particular way of arguing, but it is completely sound. That's what the truth of the matter is, and that is why people are unique and unpredictable, and although they're determined by the laws of physics like everything else, they're inherently unpredictable. And this is why we use terms like free will, or at least why I use a term like free will, to label this unusual quality that people have that sets them apart from all other known systems in the universe. Not merely other animals, everything else we know of. Everything else we've hitherto been able to create, generate, explain. Okay, so once we can explain ourselves, how it is we go about generating these explanations, still we won't be able to predict the future content of our knowledge, but we might have whatever the algorithm is that is able to generate explanatory knowledge. And then we'll have the algorithm for a person, but even then we won't be able to predict what that person will do. That person will have a creative capacity to generate explanations, or free will, whatever you want to say. Anyway, going off on my hobby horse again, that's where we'll end it for today. There's still more yet to read in this chapter, problem solving. This all-encompassing, really, vision, not only of science, but, as Popper said, all life is problem solving. All of the different areas of our intellectual life that we're interested in, our personal life that we're interested in, and just all the ways in which we might want to make progress personally, as a community, as a civilization, is encapsulated by this problem-solving enterprise, rather than a search for final truth, which would be an end of science, an end of knowledge creation. We don't expect that. We just expect to continually solve problems. That's the way to find contentment in the world, to continually solve your problems. That's fun. Finding solutions continuously and then finding new problems that are more interesting. That's one of the meanings of life. Okay, until next time. Bye-bye.